All right, we're now going to be talking about rates of change and how derivatives are applied to rates of change. Okay, so everything that we've done so far with derivatives, we've applied to curve sketching and kinematics. But what are some other real-world uses of derivatives? Okay, well, pretty much anything that can be modeled as a function of time, okay, where the function's continuous, is a possible situation where we could use derivatives. Okay, for instance, temperature. Temperature can be modeled as a function of time. Okay, how fast is the temperature changing with respect to time? Okay, how fast is a tree growing with respect to time? How fast are stock prices changing? Okay, so I could model these situations, okay, as functions of time, and then the derivative of those functions would tell me the rate of change, the instantaneous rate of change at any instant of time. Okay, and in this box I would put t, a big T, h, or p. Okay, depending for these situations. And we say that the rate of change is this symbol, right? So it's exactly the same. You know, everything we've done so far has been ds dt or dv dt, and it's just a change in notation. All right. But so we can do anything that relates to time, okay? But also any other mathematical situation where my independent variable is not time can also be derived, as long as it's continuous. Okay, here's some other examples. Area and volume. If I can write area as a function of volume, or volume as a function of area, then I can differentiate that with respect to the independent variable. Okay, so if I have a as a function of v, then I could say, well, the rate of change that the rate at which the area is changing with respect to the volume, okay, as I change the volume, how fast is the area changing? I could use derivatives to calculate that. Oops. Okay. Same thing here with this example. If I had a cost and number of items, okay, and I could somehow create a relationship, a function between these two, and this was, let's say, x, and that was my independent variable, then if I can write it as a function, I can take the derivative of that, okay, mathematically. It's just possible since I have a function, okay? So dy dx would be the general form, okay? I can take the derivative of any variable with respect to the independent variable, okay, as long as it's a continuous function. As long as it's a smooth curve and there's no, you know, as long as it looks something like this, or there's no big undefined points, okay, like this. As long as it doesn't do that, or you know, it doesn't do something like this, and it's not very continuous, okay. Then as long as it's continuous, we can take the derivative of it, okay. And we say dy dx is the rate of change of y with respect to x. All right. Okay, so let's look at one example. Let's say that we ask a psychologist to give us some data about the ability of a person to understand spatial concepts. Okay, so let's see, what does this mean? Spatial concepts, okay, some kind of space-related concept. So can they understand putting together a three-dimensional puzzle, or can they understand throwing a ball and understanding the concept of depth? Okay, so if we say to this psychologist, can you give us some data about the ability of the person, okay, and let's say we could measure the ability with a number, okay, so a person with a ability of 5 can understand a certain amount of spatial concepts. So they've quantified it. If we can say, give us that data and also give me the age of that person. So now I have two sets of variables, the ability A and their age, and let's say I could create that with relate those two with a model. If I say A is equal to 1/3 square root of t, okay, let's just say that is the model, okay. Well, what can we do with this information, right? And also, let's say that the t is in age in years and time is between 5 and 18. So we're only looking at the age group between 5 years old and 18 years old. Okay, so given this model, find the rate of improvement in ability to understand spatial concepts when a person is 9 years old and when a person is 16 years old. Okay, so if you're having a little bit of difficulty with this question, understanding what it is, pause the video, read it again, and then listen to this explanation. Okay, so this says find the rate of improvement in ability. Rate of improvement in ability. Okay, so if A is ability, how fast are they improving, basically, right? So really what that's asking for is, since I know A is 1/3 root t, what is dA dt? Okay, so they're saying how fast is the ability changing relative to their age, okay? And then basically they're saying, well, what's dA dt when t is 9, okay? So that's really what this question is asking. And then this part's asking, well, what's dA dt when t is 16, okay? So we need to find dA dt, and we can do that since this is 1/3 times t to the 1/2, okay? If I take the derivative of that, well, dA dt then just becomes 1/3 times the 1/2 in the exponent comes down to the front, 1/2 t to the minus 1/2. I simplify that and I get this function, 1/6 t to the minus 1/2. And then I just plug in t equals 9. Okay, I evaluate that when t is 9. Okay, and if I do that, I get the rate of change when they are 9 years old to be 1/18 units per year. Okay, and I've just said units here because we don't know what exactly this number means, right? We don't exactly know what area means, what that number means. So we're just going to assume that it's in some sort of unit. And so that's why we say this, okay? So 1/18 tells me how fast their ability, quantified number, that number is changing relative to the year at that instant, okay? And same thing with part 2, dA dt when t is 16 is, I just plug 16 into my dA dt formula, into this formula here. And I get 1/6 times 1/4, and that turns out to be 1/24. Okay? Now, explain why dA dt is greater than 0 between the ages of 5 and 18. Why is this number always going to be positive for this interval? Okay? Comment on the significance of this result. So in this section, you're going to be doing a lot of interpretation of derivatives. And I think this is a great exercise because you're not just doing the derivatives anymore, but you're actually having to think about why it matters. Okay? Why is dA dt positive between this interval? And then comment on the significance. All right, so mathematically we have to show why this is positive. All right, so how do we do that? Well, if I find the sign diagram of this, maybe I can use that to explain why it's positive. Okay. Well, let's see. dA dt is really this function. Is there any number that I can put into t that will make this negative, where t is between 5 and 18? Okay, any number between 5 and 18 that I put into here will always result in a positive derivative. So since t is always positive on this interval, dA dt is also positive. Okay, so that's the mathematical reason for this. Now, what's the significance of this result? Let's think about what dA dt means. dA dt is, okay, dA dt is the ability, the rate at which a person's ability to understand spatial concepts changes. So if it's positive, that means that A, what's happening to A? If dA dt is positive, A is positive, right? A is positive. It's increasing. Sorry, not positive, but it's increasing. Okay? So that means that the ability is increasing over time. Okay? Over this entire interval. The ability to understand spatial concepts is always getting better between the ages of 5 and 18. Okay? So that's kind of an interesting result. Okay? That's good. That's hope. There's hope for you since if you're not 18. Okay? So your ability, if this model is true, your ability to understand spatial concepts will keep getting better until you hit 18, according to this model. Okay? Now, explain why the second derivative is going to be 0 on this interval, and then comment on the significance of that. Okay, so what is the second derivative? Second derivative, mathematically, we've learned, tells me the concavity of my original function. It tells me the concavity of A, doesn't it? Okay, so let's show that mathematically, that it's got to be concave down since that's negative. Okay, so dA dt is this function. If I take the derivative of that again, I'm just applying the power rule and constant multiple rule one more time. So I get 1/6 times negative 1/2 t to the minus 3 over 2. And notice that this is now a negative number. This part is still, since my t is always positive, this part is still going to be positive. Okay, so my net number is negative. And so, oops, that should say negative, sorry. That should say negative. Okay? So what does that mean? What does that mean if this is always negative? So I've shown this part to be true. Now let's comment on the significance. Well, it's kind of like the acceleration. The second derivative is kind of like the acceleration, but it means, in this case, also, the second derivative tells me how fast my original rate of change is changing, right? And since it's concave down, since it's negative, okay, it says that my dA dt is going to become, is decreasing. It's saying this is decreasing, which means the rate at which the ability to understand spatial concepts increases. So it's still increasing between 5 to 18, but as I go closer to 18 from 5, the rate at which I learn is going to slow down. Okay, my ability to learn is going to get slower. Okay, so I learn slower as I get older. Okay, so even though the good news is that you will, if this model is true, that you will learn better as you will keep learning as you get older. The ability, the rate at which you learn is gonna be slowing down. Okay, and that sort of makes sense too, because a 5-year-old will probably pick up stuff a lot, soak in a lot more information than an 18-year-old would. Not necessarily true, but you know, they say that, you know, if you're really, really young, you learn faster, right? Okay, so that's hopefully you can think really deeply about the context and comment on the significance of different different results that you get.